For the rest of section 6.6, we will turn our attention to more complicated exponential equations. Before we do that, we are going to go back and review the basic exponential equations that we learned how to solve in section 6.3. That method is summarized in this box, which is at the bottom of page 4. If you remember, first of all, how do you recognize an exponential equation? Well, it's going to have an equal sign, meaning it makes sense to solve for x or whatever variable you're using. And the other thing that has to happen is x, the variable, has to be in the power or the exponent, okay? So the method we learned back in section 6.3 was getting the same base. Remember, the base is what you're raising the power to, okay? Getting the same base on both sides of the equation. And then once you had the bases equal, you would equate the exponents or the powers and then go from there, okay? So we're going to do a quick review of that, and then we're going to get into more complicated exponential equations. And what I mean by more complicated is there's no way to make the bases the same on both sides of your equal sign. Okay, so we're talking about how you would solve something like that. Okay, all right, so let's do a quick review of basic exponential equations. Okay, so I am looking at example 4 in your notes. This is at the top of page 5. Okay, so example 4 says to solve each exponential equation, express irrational solutions in exact form, meaning no decimals, and as a decimal rounded to 3 decimal places. Okay, just remember irrational means it's a funky looking answer. So anyway, okay, let's look at example A. Okay, 5 raised to the negative x power is equal to 25. Okay, so what is going on here is that this is an exponential equation. Okay, when you look at this, the x is in the power or the exponent. Okay, so what we tried to do in section 6.3 was to make the bases the same on both sides. Okay, so if you look at the left side, the base is 5 because that's what you're raising to the power. And on the right side, the base is 25 because you're raising 25 to the first power. Okay, so the bases are not the same here, but you can actually make them the same. So remember, usually you're going to want to try to change the bigger number into the smaller number. So we're going to leave the left side alone. And then you want to rewrite 25 using the base 5. Okay, so what you can do is you can say, okay, what power do I raise 5 to get 25? That's the second power. Okay, 5 squared is 5 times 5. That's 25. Okay, so now on the left, I have base 5. On the right, I have base 5. So once the bases are equal, the only way this can be true, okay, is that, if you have a power of 5 equal to a power of 5, the powers have to be equal. So you're going to equate the exponents like that. So negative x equals 2. And then you just solve this for x. Okay, so this is negative 1 times x is equal to 2. So we're just going to divide or multiply by negative 1. Okay, and so this is going to tell us that our x value is negative 2. Okay, so that's all you have to do there. Okay, remember we just came out of logarithmic equations and you had to check your answers with logarithms or the logarithmic equations. You do not have to do that for exponential equations. Okay, the reason you have to do it for logarithms is because you can't take the log of a negative number or of 0. So you have to watch out for that. There's a domain issue there, but the domain of an exponential function is all real numbers. So even if you got something negative, you could still plug it in, okay? So you don't have to check your answers for exponential equations, just for logarithmic, okay? All right, let's try the same method on part B, which is a little more complicated, okay? I've got 4 raised to the 5x power is equal to 32 raised to the x minus 1 power, okay? So this is exponential. The x is in the power. Okay, you've got an x on both sides, actually. So, we're used to trying to take the bigger number and writing it as a power of the smaller number. So if you try to write 4 to what power is going to give me 32? Well, 4 to the first power is 4, 4 squared is 16, 4 to the third power is 64, so it doesn't work. So actually what you have to do here is you have to change both of these. Okay, you're gonna have to change both of the bases. Okay, so we can actually write both 4 and 32 as a power of 2. So that's what we're going to try here. And I'm going to go ahead and color code this. All right, let's rewrite the equation to start off with. Okay, I'm going to put 4 in green because we're going to have to change that base. Okay, it is currently raised to the 5x power. And that is equal to 32, I'll put in pink. That is currently raised to the x minus 1 power. Okay. Because we cannot write 32 as a power of 4, we have to change both of the bases. Okay, like I said, they can both 4 and 32 can be written as powers of 2. Okay. All right, so let's work on the left side. Okay, and then we'll come back and work on the right side. All right, 4. We're going to try to rewrite it as a power of 2. Okay, 4 is 2 squared. Okay, so what's in green is the same thing. Okay, 4 is the same thing as 2 squared. Okay, 4, whether it's written as 4 or as 2 squared, it has to be raised to the 5x power. Okay, so that is what the left side is going to become. Okay, and then you have to apply, you have to simplify your exponents before you can go on. Okay, you have to apply the laws of exponents. You have a power raised to a power. Okay, when the exponents are side by side like this, remember, you need to multiply the exponents. So this is going to become 2 to the 10x power. Okay, and now that's simplified. That is now the left side. So we're going to move on and try to convert the right side to a power of 2. Okay, all right, 32. What power do you raise 2 to get 32? 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth, 2 times 2 times 2 times 2 is 16. 2 to the fifth gives you 32. Okay, so what's in pink is identical. 32 is the same thing as 2 to the fifth. Okay, this quantity 32, when it's written this way, it still has to be raised to the x minus 1 power. Okay, so I'm using parentheses here because this quantity has to be raised to the x minus 1 power. Okay, all right, in the next step, you need to simplify your exponents. Okay, same thing that was over here. You have a power raised to a new power. The exponents are side by side, so you multiply them here. You've got to be careful here because it's 5 times the quantity x minus 1. That 5 is going to have to get distributed. Okay, so we're going to end up with 2 raised to the 5x minus 5 power. Okay, so be careful there. You have to distribute the 5. Okay, all right, so the left is 2 to the 10x. Okay, all right, so now I have 1 power of 2 equal to 1 power of 2. Okay, so the only way that this can be a true statement, a power of 2 equal to a power of 2, is if the powers are equal. Okay, so we're going to go over here and we're going to equate our exponents. So 10x has to equal 5x minus 5. Okay, this now is an equation we know how to handle. It's no longer exponential. X is out of the power. All right, this is actually linear. The highest power of x is 1, so we just need to isolate the x. So we're going to start by putting all the x terms on one side. So I'm going to move the 5x over. So I'm going to get 5x is equal to, these guys cancel. Okay, so 5x is equal to negative 5. Okay, divide both sides by 5. And I get that x is equal to negative 1. And that's my answer. Okay, all right. So that was just a quick review of solving exponential equations where you can get the same base on both sides. Now we're going to venture out and look at more complicated exponential equations, meaning that is not possible. We're going to have equations where there's no way to get the same base on both sides. And actually, what you're going to have to use is a logarithm.